get started here in a minute. Continuing on talking chapter 4, and then we'll go on to probably chapter 5 as well. Again, if you have questions, feel free to ask in the chat box there. Good morning. All right, we're going to continue on here talking chapter 4, and we were talking bonding. So we finished up last time talking about how to draw Lewis structures. So again, you want to follow those steps to draw Lewis structures, and should lead you to the correct structure if you follow those kind of steps in order. So where we left off here, I think, is right about here. So we're just going to talk about a couple of things here in terms of molecules and bonding. First off is bond length, and that is the distance between basically two atoms within a bond. And if we look at this chart, and you don't have to obviously memorize any of these numbers or anything like that, but if we look at these charts, this is our carbon-carbon single bond, double bond, and our triple bond. The length or distance between the two atoms go from 154 to 133 to 120. Same thing here if we look at our carbon-nitrogen bond, single, double, and triple, 143, 138, and 116. And what we generally see here is as we continue to add a bond, the distance between the atoms gets smaller. So, a single bond here, longer than a double bond. So as we put that double bond into place, very badly drawn double bond there, the distance between the two atoms get closer, they get pulled together. And if we made a triple bond here, they get smaller as well. So every time you pretty much add a bond on there, everybody's going to get closer together. And that does relate to sort of strength and length. So if we look at sort of that relationship, here we see that the bond strength is really a triple bond is stronger than a double bond, and a double bond is stronger than a single bond. A triple bond is not like 3 times as strong per se, but that's the general trend, and it does relate to sort of bond length. I usually think about it as like a pencil. You get a brand new pencil out. It's nice and long. If you wanted to, you could take it, you could snap it pretty easily. If you've taken the same pencil after some chemistry test or something like that, and all you got left is a small nubbin and an eraser, basically of the pencil, it's much harder to try to break that apart. And that's sort of the way the bonds work as well. Again, as everybody gets closer to each other, everything is sort of locked into place tighter and making for a stronger sort of bond. So triple bond, much stronger than a double, double stronger than a single bond. Now we talked a little about resonance structures as we were drawing those Lewis structures. And remember, basically a resonance structure is a structure where, for example, you have the ability to make the double bond or maybe a triple bond in a different location. So for example, when we looked at our carbonate that we drew, we double bonded up on top, but we could have double bonded. We could have double bonded over here. Little thing's going crazy today. There we go. Could have double bonded on this side. Oops, single bond there. And again, top one here is a single bond. And we could have double bonded to the other side as well. And again, that would have gave us a 3 different structures that you could draw. So when you have sort of the ability to draw a resonance structure, if you have more than one place where you could put that double bond, you would want to move it to the next one. And they're pretty much equivalent structures to each other, so they basically represent the same structure. And if you're not asked to draw resonance structures, you could just draw one of those type of structures. You don't have to draw all of them, but any one of those would be a good structure. So here's just some examples. The carbonate, like we saw last time, a better drawing there. Again, you can draw 3 different resonance structures. The only difference between these structures is basically where the double bond is located. And again, if you're not asked to do that, which you probably won't be in this class, you could draw any one of these 3 structures and it would be perfectly fine. The benzene ring is really just something that looks like this. It's an organic molecule. And you can make your double bonds in that location. You could also do some double bonding going this way. And these are resonance structures which are why oftentimes you'll see benzene drawn. You ever seen benzene? Yeah, it looks like a circle in the middle. And that represents that those really double bonds can kind of move around at any given point. They could be in different locations. Any questions on resonance structures, which I think we kind of talked about as we were drawing the Lewis structures. All right, and again, you don't have to draw resonance structures unless you're asked to do so, and I don't think I'm going to ask you to do so, so you probably will be all right. So we did talk about the octet rule, and pretty much for our class, everything will obey the octet rule. So if you're asked to draw any type of Lewis structure, it should obey the octet rule. But you should be aware of that there are some exceptions to the octet rule that you sometimes come across. And we're just going to talk about these exceptions. You won't be asked to draw any of the exceptions. Again, everything that you draw should obey the octet rule. And you never trust Adam. They do make up everything. Good joke. I like it. So so the first sort of exception to the octet rule is the incomplete octet. The incomplete octet is when we have actually less than 8 electrons around it. So less than 8 electrons around it. So something like beryllium hydride, which we have on the screen here. This one right here has only 4 electrons around it. So it does not need 8. It's perfectly happy with it. Really, the most common one that you see have less than 8 is something that has boron in it. So somebody that has boron, like we got down here, also very commonly makes an incomplete octet. So as we can see here, boron trifluoride, it has only 2, 4, and 6 electrons around it. So 2 more exceptions to the octet rule are an odd number of electrons. And again, we won't come across this in this class, but an odd number of electrons basically means that you don't have a pair of electrons. You'll end up with 1 unpaired electron like we see here in NO. And we see over here in NO2 as well. We'll end up with only 1 electron that's not paired. Those are things that are sometimes referred to as free radicals. You see a lot of it in atmospheric sort of chemistry with chlorine and stuff like that. These guys are very reactive because of that, because they're missing. They only have kind of 1 electron, an unpaired electron. Doesn't really like to be like that, so they're very, very reactive sort of species. Now, if you continue on in chemistry, the one exception that you will see the most outside of this class, in the next class, whatever they call that here, 1A maybe, or whatever that class is called, is the expanded octet. And the expanded octet is molecules that can have more than 8 electrons around it. And that's a very common exception that you see a lot, especially, again, if you kind of continue on to first semester general chemistry, you'll see it all the time. And if you look on the periodic table, where we usually see the ability for that to occur is right where sulfur is. So right where sulfur is, kind of to the right, to the left, and down from where sulfur is. They have the ability basically to do that. They have the ability to go over 8, which is why very commonly, if you ever kind of look around, Google things or those type of things, and you look at Lewis structures that involve sulfur, if you count up, a lot of times you'll see it going over 8 very commonly. The reason they're able to do that is because of where they are on the periodic table. That's on period 3, which means n equals 3 in this case. And when n equals 3, the orbitals that we have available to them are s's, p's, and that's when we first start to see the d orbitals basically available to them. And remember that although they may not be using those d orbitals, because they do have it available to them, they're able to basically stash those extra electrons up in the d orbitals. So very commonly something like sulfur, and again, if you look on the periodic table to the right and left of sulfur and down, they have that ability to go above 8, and they're perfectly fine with that. And that's the expanded octet. And again, that's one that you'll probably see the most as you continue on in chemistry. You see it a lot in sort of the first semester general chemistry class. All right, so for us, those are the 3 exceptions to the octet rule. You just need to know what the 3 exceptions are: an incomplete octet, an odd electron molecule, and an expanded octet. Again, anything that you're asked to draw in here will obey the octet rule, and you should obey the octet rule. Any questions on that? Okay, so we're going to talk about molecular geometry and some polarity. And I know in lab, I believe she's gone over it. So we're just going to make sure we hit all the fine points here, make sure everybody's on the same page. When we talk about molecular geometry, the good news is it's not really math or anything like that. It's basically kind of the 3-dimensional arrangement of these molecules in space. We can sort of predict the geometry of a molecule based on its Lewis structure. And especially when we get into molecules that have more than 2 atoms involved, we could predict that geometry based on the central atom. So usually when you do geometry, it's always sort of the central atom that's really the most important when you do it. And the way we're able to do this is it's based off of the idea of electrons, and electrons which are negatively charged. And since they are negatively charged and they're involved in bonding, no matter what happens when you make bonds like covalent bonds, those electrons do have to be near each other. And because they are essentially negatively charged, they really don't want to be near each other. So they will try to basically get as far apart as they can from each other because they're negatively charged. And the problem is they really can't truly escape each other because they're locked into a bond. But as they're trying to move to get that distance from each other, we do get sort of different shapes that occur for molecules depending on the types of electrons that are involved. And this approach is what's known as VSEPR, VSEPR, which stands for valence shell electron pair repulsion model. That is probably why they abbreviated. That is a mouthful there. And it basically accounts for the geometry that we see when we draw these Lewis structures and we think about these molecules. And when we look at them, as we'll go through this here, they're really divided into sort of 2 different parts. One part is where we have a central atom that does not have any non-bonding electrons or lone pairs. And one, when we look at the central atom and draw the Lewis structure, we see some of those non-bonding electrons basically occur. The couple of things to think about when you do geometry is the first one is really the most important here, which is down here. So when we are doing geometry, no matter whether you have a double bond, a triple bond that you draw, these count as one electron pair and one bond. So that's really important when you're doing geometry. And again, only doing geometry. If you have a double bond or a triple bond, it doesn't matter in terms of this geometry. You want to count it as only one electron pair and also one bond. When we talk about names, we're going to see two types of names. One is the electron pair geometry, and that describes how the electrons are arranged around the central atom. And the other one is the molecular geometry, or that is sometimes referred to as the shape. And that describes the overall arrangement of all the bonds as they come together and what the shape of the molecule is. So we're going to talk about two different names as we go through this, and make sure you keep that in mind. So let's take a look here. So first off, let's just talk about really the simplest geometry that you could do. And the simplest geometry that you could have are these diatomic molecules. So these diatomic molecules are really the simplest ones that you could have. Those again are the ones that have only two guys together. So like F2, H2, even HF, they don't have to be the same. HCl. All these guys that pretty much only have two atoms involved. The geometry is pretty simple. The only way you can arrange two things is in a straight line. So the geometry is linear. And you don't even have to think about it, whether it's a single bonded thing, whether you got like a double bond like you got in oxygen. It doesn't matter either. It is going to be a linear molecule. You could have a triple bond like the nitrogen that we drew last time. As well. So it doesn't matter. Two things, just put linear, move on, you'll be good in terms of geometry. Now, when we do get to things that actually have three or more atoms involved, we do have to look at two things. And the two things that you want to look at is you want to look at the number of electron pairs around the center atom. And you want to look at the number of bonds also around the center atom. So when you're doing these guys, there's geometry and stuff for things that have multiple bonds, multiple atoms, three or more. You want to look at the center atom, how many electron pairs and how many bonds. So here, if we look at Be, which is our center atom, it has 1 and 2 electron pairs. And it also has 2 bonds when we look at it. So something with 2 electron pairs and 2 bonds, because there's only those 2 guys that are happening, they will basically spread out as far apart as they can, and we will get a geometry of linear for the electron pair. And it will also be linear for the molecular geometry as well. So the name will be the same for both for this. So linear would represent the electron pair geometry when you have 2 electron pairs and 2 bonds. And it would also represent the molecular geometry. So as you can see here, they end up spreading out 180 degrees from each other. So those two bonded guys are able to spread far away from one another, which in this situation makes it really happy because there's nothing else to get in the way. The next one that you have is something like BF3. And in BF3, if we look at the central atom, the central atom has 1, 2, and 3 electron pairs. And it also has 1, 2, and 3 bonds. So something with 3 electron pairs, the electron pair geometry is what is known as trigonal planar. And the molecular geometry is also known as trigonal planar. It essentially makes and molecular geometry is also trigonal planar. It essentially makes, if you look at it, a triangle. So if you look at this guy here, essentially makes a equilateral sort of triangle. And it has a bond angle of 120 degrees here. So something with 3 electron pairs and 3 bonds is what is known as trigonal planar. And that it describes both the electron pair geometry name and the molecular geometry name, which would also be trigonal planar. Now, trigonal planar is sometimes called triangular because it does sort of make that triangle type of shape as well. And again, the bond angle is 120 degrees. The next geometry that you have to worry about is something that basically has a central atom and 4 bonds to it. And when we look at the central atom here, which is carbon, it has 1, 2, 3, and 4 electron pairs. And with 4 electron pairs, it also will have 4 bonds. So electron pairs is 4. Bonds is 4. So it's with 4 electron pairs and 4 bonds. The electron pair geometry is what is known as tetrahedral or tetrahedron, but most people nowadays call it tetrahedral. And the molecular geometry name is also going to be tetrahedral. Will be the same, so it'll be tetrahedral as well. So in this particular case, because we have these 4 bonds, they sort of spread out almost like in a pyramid shape, and then on each of the sides it makes like a triangle type of shape on each of those sides, and that's more of a pyramidal shape, and it ends up being 109.5. So something with 4 electron pairs and 4 bonds. The electron pair geometry will be tetrahedral, and the molecular geometry will also be tetrahedral. Now, up until this point, if you've seen what we've been talking about, both of these names, the electron pair geometry name and the molecular geometry name, I apologize, my pen is going crazy today. So the molecular geometry name, which is tetrahedral, they are the same. And that occurs, both of those names will always be the same for the last 3 examples that we did there. They're both the same. When we draw the Lewis structure, and our central atom pretty much has no non-bonding electrons. So pretty much if you draw a Lewis structure and there's no dots, so no non-bonding electrons. On the central atom, both of these names, electron pair geometry name and the molecular geometry name, will be exactly the same. It is only when we start getting non-bonding electrons on the central atom that we get some different interactions. So in these ones that we talked about now, the only type of electrons that we have going on around that central atom, these are all bonding electrons. They're all involved in bonds. So all these are bonding electrons. So bonding electrons near bonding electrons are, okay. They're happy to sort of be there-ish. They're not so bad. But when we start introducing some non-bonding electrons and you start to get those dots around the central atom, that's where we start to see some differences in these names. We'll see some differences in both the electron pair geometry and the molecular geometry name. And really the only one that will basically change is this name. So as we start to draw Lewis structures that have dots around the central atom or there's non-bonding electrons, that's where we start to see the molecular geometry name change. The electron pair name will still be the same regardless because there's still the same number of electrons, but we will start to see that difference in the molecular geometry name. And let's take a look at some of those. And again, this is basically the reason why is because we get these different types of electrons that are involved. So this over here is basically non-bonding electrons near non-bonding, which is the worst sort of interaction you could have. So in your Lewis structure, that's like when you have two pairs of dots near each other. They want to get as far away as they can. The kind of middle road of like not so great, but maybe it's all right, is when we get some non-bonding electrons near bonding. So in your Lewis structure, that's like dots near lines. And the best situation is sort of what we were talking about previously in the first few, is bonding electrons near bonding electrons, no dots involved in the structure. That is where we see the names the same. So when you draw that, we get those same names for those geometries. But in this situation, when you have these situations over here, that's when we start to see a different name for the molecular geometry. So let's take a look at some examples of that. First one is SO2. And if we draw SO2, which is apparently not here, but if we draw SO2, which we might have done last time, it will look something like this. And if we count up how many electron pairs it has, this has one here. It has two here. So when you're counting electron pairs, doesn't matter if they're lines, doesn't matter if they're dots. It's just around the central atom is what you want to look at. So our sulfurs are central atom here. Then the last pair of electrons is found right here. Now, this is a double bond, but it only counts as one electron pair. So remember, double bonds, triple bonds in geometry only counts as one electron pair. So that is 3 electron pairs. It also will have 1, 2, and again, our double bond will count as only one bond. It will have 3 bonds. So in terms of those names, the electron pair geometry name here will still be trigonal planar. And the reason it's trigonal planar is just like before, it still has 3 electron pairs total around the central atom. So the electron pair geometry name doesn't change. But in this case, we have a couple different types of interaction. We have bonding electrons near bonding electrons. We have non-bonding electrons near bonding electrons. So they try to get away as far apart as they can from each other. And the molecular geometry name, or the shape, becomes what is known usually as angular. Some people call it bent angular. Some people may even call it bent or bent angular, but angular as well. It has a bond angle of a little bit less than 120 degrees. The bond angle is based on the electron pair geometry. So 3 electron pairs is trigonal planar, which is 120 degrees. But because this one is not a bonding atom, it's a non-bonding atom, there's a little bit more room for those guys to kind of spread out, and we get a bond angle that's a little less than 120 degrees. So 3 electron pairs, and I'm sorry, that doesn't have 3 bonds, my bad count. It actually only has 2 bonds. Let me do that again. So in terms of bonds, it has 1 and 2. So this has only 2 bonds, but 3 electron pairs. So I apologize, that's wrong. So one more time, 1 electron pair, 2 electron pairs, 3 electron pairs. But in terms of bonds, 1 bond here and 2 bonds total here. So 3 electron pairs and 2 bonds give you an electron pair geometry name of trigonal planar and a molecular geometry name of angular. Any questions on that there? So again, only 2 bonds in this one counting as 1, and obviously this one counting as 1 as well. So that's 2. The next example that you have is something like NH3, and in NH3, when we look at it, it has 1, 2, 3, 4 electron pairs. And in terms of bonds, it has 1 bond, 2 bonds, and 3 bonds. That way I counted it right this time, right? That's good. So again, in terms of the electron pair geometry name, 4 electron pairs is tetrahedral. And in this case, we also have non-bonding electrons near bonding electrons, bonding near bonding. Because this guy has an extra sort of bond than the previous one did, it will make a shape that is known as trigonal pyramid or trigonal pyramidal. So the molecular geometry is our trigonal pyramid. And it will have a bond angle just less than 109.5, which is the tetrahedral bond angle. It's about 107-ish in this case. Kind of makes a pyramid shape on the bottom and a triangle type shape on top, which is why it's called trigonal pyramid. Now let's take a second here just to talk about 2 names that we've seen. So molecular geometry here is trigonal pyramid. When we had 3 electron pairs and 3 bonds, that was trigonal planar. So there is a difference between that. So you do have to choose and write the entire thing. You can't do, you know, my favorite answer to these questions. I think the geometry is trigonal, and let me choose. And you don't want to do that because I will choose wrong because I failed chemistry. So I will choose the wrong answer. So make sure that you choose one. Also, my other favorite is trigonal. That obviously is planar. Oh, you mean pyramid? I mean, that's pyramid. So, and between those 2 sort of geometries, make sure you write either trigonal planar or you write trigonal pyramid. Do not just write trigonal because it will get a big X like that. Yeah, so make sure that you do choose. Any questions on that one? And our last geometry here is one like what we see in water. So when we look at water, it has 1, 2, 3, and 4 electron pairs. It also has 1 and 2 bonds. So our electron pair geometry is going to be tetrahedral as well. Again, because it still has 4 electron pairs. Doesn't matter if they're bonding or non-bonding. But in this situation, we have all of the 3 electron happening. We have bonding electrons, which are here. So bonding electrons near bonding electrons. We also have non-bonding electrons near bonding. And lastly, we have the worst situation, non-bonding electrons near non-bonding electrons, so dots near dots. So what happens is really when this guy comes together, those non-bonding electrons pretty much try to go as far as they can, kind of this way, to spread out. But as obviously these guys move, so where our bonded guys move as well. And what we end up getting for the molecular geometry for something like water is what is known as bent are V-shaped. And again, that's why you will typically see water drawn like that in that sort of V-shaped or bent way. And again, in this case, it has all of the worst sort of situations occurring. So as you can see here, the electron pair geometry name will be consistent, and it is solely based on looking at the central atom and how many electron pairs you have around it. The name that could change is the molecular geometry or the molecular shape is sometimes referred to. And again, that really does depend on whether or not the type of electrons that you have around that central atom. Any questions on that there? Okay, so here's a table. I'm not sure this one's from your book, but you have a similar type of table. And this really is sort of the best way to kind of do it. You want to think about basically electron pairs, which is really what this column here is, how many electron pairs, and this is basically how many bonds. That's how many bonds, how many electron pairs. And again, it's always the center atom that you want to look at. And you can see the shape here. This would be what is known as the molecular geometry shape. Not on this table is electron pair geometry, but the molecular geometry or the shape is on this table there. Any questions on how to do that? So for us, you do need to know electron pair geometry name and the molecular geometry name. You don't have to worry about bond angles for us, so you don't have to worry about bond angles or anything like that. Any questions on geometry? Okay. And if you do, feel free to type it and I'll get to your question. But just to finish up on this chapter, we're going to talk about polarity. And what we're talking about here is what is known as molecular polarity. And in molecular polarity, it is really different than what we were talking about when we used electronegativity and bond polarity, but it is represented really the same way. Sometimes it is represented with those sort of arrows. If you remember, we had those arrows, which were those bonding arrows, those dipole arrows, and those dipole arrows remember points to the more negative side, and the more positive side is where the other side of the arrow points to. So when we talk about polarity or molecules being polar, it really does depend on a couple of things. But let's talk about sort of the easiest ones to determine polarity. And the easiest ones to determine polarity really are diatomic molecules. So whenever you have a diatomic molecule, they're very simple to sort of determine if they're polar or not. So for example, if we took something like F2, when we look at this bond between F2, you look at this bond and know that it is a non-polar bond. And that is, again, based on their electronegativity. They both have a value of 4. So when we subtract them, that gets you 0. And that is going to be a non-polar bond. Now, because this is a diatomic molecule, the only bond that you have in this molecule is that bond. And since that bond is non-polar, and that's the only bond in the entire thing, the molecule would be a non-polar molecule. Now, if you look at something, say, like HF, which is also diatomic, when we look at the bond between hydrogen and fluorine, again, this is something like 2.1 in terms of electronegativity. This is something like 4, which gives you a difference of what we got there, 1.9 when you subtract it. And that would mean that this is a polar bond. And for the same reason here, because this particular bond is the only bond in the entire molecule, the molecule would be a polar molecule. So if you have a diatomic molecule, pretty much that is when you can use electronegativity values to kind of help you decide whether or not it's going to be polar or non-polar. And pretty much because it only contains one bond, if that bond is polar, then it will be a polar molecule. If that bond is non-polar, then it would be a non-polar molecule. Now, when we get to things that are 3 or more atoms involved that are not diatomic, it is a little bit more complicated. You do have to look at 2 things when we have things that are not diatomic. You do have to look at, are there polar bonds? And you also have to look at the molecular geometry. So you have to look at both the polar bonds, are they present, and the molecular geometry to see things that have 3 or more atoms, so 3 or more. So let's take a look at that when we do have 3 or more atoms. So for example, let's take a look at something like carbon dioxide. So if you drew carbon dioxide, it will look something like this. And if we look at carbon dioxide, the bond between carbon and oxygen is polar, with oxygen being more electronegative. And if we were to draw those arrows, we would draw them heading towards the oxygen as it's more electronegative. And it does have polar bonds. Now, it may have polar bonds, so you may say to yourself, well, this definitely will be a polar molecule. And that's not necessarily the case here, because when we look at the geometry here, it has 2 electron pairs and 2 bonds. And the molecular geometry, which is what you want to look at, in this case is linear. Which basically means in this case, these little dipoles, this guy is going to pull this way. I'll make it bigger. But because it's linear in a straight line, this guy is also going to pull in an equal and opposite direction, and they will essentially cancel each other out. So CO2 is a very good example of something that does have polar bonds, but the molecule itself is going to be nonpolar, because those polar bonds essentially will cancel each other out. Now, those little dipole arrows that we draw are basically vectors, which means they have direction and magnitude. And in this particular case, they end up canceling each other out. And that's different if we take something like water. Water also has a polar bond, oxygen being more electronegative. So if we drew those little bond dipoles, it would head this way. This guy would head this way. Now, it does have polar bonds, this guy. But the geometry here is bent or V-shaped, as it has drawn 4 electron pairs and 2 bonds. So the molecular geometry here is bent or V-shaped. And you could kind of imagine, in this case, they're not heading equal and opposite directions, but they kind of will add to each other. And for water, what we get is what is sometimes referred to as a net dipole moment. I apologize for the writing. little technical difficulties here. And that is what this big sort of dipole arrow represents. It has a net dipole moment. And what that means for something like water is near the oxygen side of that molecule, it's more negative. Near the hydrogen side, it's more positive because of the unequal distribution, basically, of the electrons in that entire molecule. And really what's happening in that case is those vectors, you got one coming this way, you have the other guy coming this way. And unlike carbon dioxide, they actually will add to each other and head in that upwards direction in that particular case. And that's why something like water has a dipole moment and known as a polar molecule. So there's very hard sometimes to visualize in three-dimensional space these things. So there are some geometries which are pretty much known as being symmetrical geometries. And symmetrical geometries are ones where you draw the Lewis structure. There are things like, for our purposes, trigonal planar. And also tetrahedral. And when you draw these geometries in a trigonal planar or tetrahedral, you draw them in a Lewis structure, what you will see is the main thing around the central atom, no dots. Yeah, no dots, which basically means no non-bonding electrons. So no non-bonding electrons. And if you draw a Lewis structure that has these two geometries, trigonal planar and tetrahedral, and everything attached is exactly the same, it will pretty much be a safe bet to call it a nonpolar molecule. So these two geometries, everything attached is exactly the same on the outside in terms of elements. Nonpolar is the molecule. Nonpolar molecule is pretty much the right answer. Now, if you do have these geometries and everything on the outside are not the same elements, it will go from a nonpolar molecule to a polar molecule. And that leaves us unsymmetrical geometries. And those are your angular, your bent or V-shaped, and your trigonal pyramid. Again, pyramid here, and I'm really sorry about the writing here. Pen kind of died. These guys, again, when you draw the central atom, what you're going to see are dots around the central atom. So if you draw a Lewis structure and you see dots around the central atom, which represents non-bonding electrons being there, and everything on the outside is the same, it will be a polar molecule. Yeah, so it's a pretty safe bet for it to be a polar molecule. So those are sort of the quick ways that you could do it without really thinking about everything, a lot. You can look at your Lewis structure, and if you draw a Lewis structure and it has a molecular geometry of trigonal planar or tetrahedral, and you have no dots on the central atom, everything on the outside is the same, going to be nonpolar. If you draw the Lewis structure and you have dots on the central atom, everything on the outside is the same, is going to be a polar molecule. And if you draw a Lewis structure, no dots on the central atom, everything on the outside is not the same, it will also be a polar molecule. Any questions on that? So let us take a look at the ones we got on the screen and sort of use our method here. Again, we don't have to get too complicated into this. When we look at this central atom, there are no dots. Everything on the outside is not the same. The geometry here is trigonal planar for this first one. That is our symmetrical geometry, but what makes it a polar molecule is that everything on the outside is not the same. So this will become a polar molecule because of that. And that is different than when we look at this guy here, which has no dots around the central atom, just like the first one. The geometry here is trigonal planar, just like the first one. So molecular geometry is the same for both of these. But the difference here is everything on the outside is exactly the same. So everything on the outside, exactly the same. No dots on the central atom, going to be a non-polar molecule. Coming here, we see dots on the central atom. We see everything on the outside is the same. So that's going to be an unsymmetrical geometry, which this guy is trigonal pyramid, and that will become a polar molecule. Here we see, again, no dots on the central atom. Everything on the outside is not the same. So that is going to give us a polar molecule in that particular case. Any questions on how you could kind of use really, are there dots on the central atom when you draw your Lewis structure or not, as to determine that? Any questions on molecular polarity? So again, draw a Lewis structure, no dots, everything is the same on the outside, pretty safe bet, non-polar. If you draw a Lewis structure and you see dots on the central atom, everything's the same on the outside, going to be polar. And the one exception would be if you draw a Lewis structure and there's no dots, but everything on the outside is not the same like what we have here, it will become a polar molecule. And that will cover you pretty much for all the geometries that you need to do, except for linear. So since linear is basically a straight line, if you have a linear geometry, molecular geometry, you do have to look at it. In some cases, like CO2, those arrows will head in opposite directions, like two people pulling on a rope in opposite directions. The rope's not going to go anywhere if they're pulling equally. But you could have a linear situation where everybody is heading in the same direction. So everybody's heading in the same direction. And then in that case, it would be a polar molecule. So really linear, you just have to look at it, but linear is kind of the easiest one to determine. And the way you could think about linear is like pulling on a rope. So if you have two guys that are pulling equal and opposite of each other, nothing's going to happen. It's going to be a non-polar molecule. If everybody's pulling in the same direction, like on a rope, the rope will move, right? And it would become polar. So this would be a polar molecule. A situation like CO2 would be a non-polar molecule. Any questions on molecular geometry there? Okay. Bad chicken. And that should wrap up chapter 4. Any questions on that? All right. I'm going to stop sharing for just a sec. I'm going to, we're going to move on to chapter 5, I believe. All right. Perfect. All right, so we're going to move on to chapter 5 here. If I could find where I put it. Okay. Oops. Give me 1 second here. All right, let's see if that will work here. All right, maybe it likes it. Let's see. All right. Might have worked, maybe. Probably not. Let's see. Sorry about the technical difficulties today. Let's see here. All right. There you go. I think I got the right one. All right, we're off to chapter 5 now. Technology. Good today. All right, so in chapter 5, we're going to talk about chemical reactions, balancing equations, and all those type of things, doing calculations from equations. So again, these notes are up online if you need them or you haven't found them. The first thing we're going to do is talk about equations and chemical equations and sort of how to balance them and sort of different parts of it. So up on top here, we have 2H2 goes to O2, forms 2H2O. And this is what is known as a balanced chemical equation. And when we do use a chemical equation in chemistry, always, you want to make sure it's balanced. So what does that mean? It means that on the left-hand side, if we just kind of look at the elements involved, on the left-hand side, there's 2 times 2, which is 4 hydrogens. On the right-hand side, there is 2 times 2, which is 4 hydrogens. On the left-hand side, there are 2 oxygens. On the right-hand side, there is 2 times 1, which means 2 oxygens. So it is balanced, and that's what we expect based on conservation of mass. When we do a chemical reaction, which is a chemical change, we never lose any elements along the way. So really the only thing that happens is everybody on the left-hand side of the arrow pretty much breaks apart and comes back together on the right-hand side of the arrow to make new bonds and new sort of compounds and substances. And we don't lose any, which means, like in this case, since we started with 4 hydrogens on the left, they may be in different sort of compounds. We end up with still 4 hydrogens on the right, which also may just be in different sort of molecules and so forth. So we never lose any elements along the way. Elements are conserved in a chemical reaction. And when we use an equation, that's why we balance them. On the left-hand side of the arrow, that is what is known as the reactants in a chemical reaction. So on the left-hand side, we have our reactants. So that would be over here, these guys. These are our reactants. And that's your starting material. And on the right-hand side of the arrow, you go to your products. And that is the stuff that is formed as a result of a chemical reaction. And a couple other things that you commonly will see in balanced equations. You'll sometimes see next to formulas an S written. You'll sometimes see an L written. You'll sometimes see a G written. And you'll sometimes see an AQ written. And these represent the states of each of these guys. So S is solid, L is liquid, G is gas, and AQ is aqueous. And aqueous means basically a water environment. And basically what that means is you made a solution. And that's the difference between something like L and something like AQ. L implies a pure liquid. So for example, if you just took water by itself, nothing else in there with it, that would be considered a liquid. If you took water and then added some sodium chloride to it, like salt, that would make a sodium chloride solution, and that would get the aqueous symbol. So liquid is just one sort of substance by itself, like water, nothing else mixed in there with it. While something that's aqueous is basically what is known as a solution, and it's usually made a lot of times by taking something, say like sodium chloride, that's a solid, and dissolve it in something else like water. And then once it dissolves, it makes a solution, like basically of salt water. Other things you'll sometimes see on top of the arrow, for example, you'll sometimes see some things written. You'll see delta, which usually means heat. You may also see something like platinum. You may see something like H plus written on top of the arrow. These guys are what are known as catalysts. A catalyst is not a reactant. It's not a product. It is not used up during the reaction. Sometimes a catalyst is just added to a reaction to make it occur faster. So usually a catalyst will speed up a chemical reaction, but again, it's not considered a reactant and it's not considered a product. And again, it does not get used up in the reaction at all. So it's still there when the reaction's over. So very common on top of the arrow, they'll sometimes write things like that, which represent catalysts. You'll also maybe sometimes see H2O written on top of an arrow, and that would indicate that something is being dissolved in water. So these are some other things that we sometimes will see in a chemical equation. So we're going to talk about some steps to balance equation, and these are just some of the steps that you can follow, but we'll kind of go through them and see how we typically will do it. To balance a chemical equation, if you happen to be given everything in words to begin with, you want to write the unbalanced equation. And if you're given things in words like, hey, hydrogen gas plus oxygen gas forms water, you want to first start out with the correct formulas for each of those substances. Don't worry about the balancing part. You just want to basically get all the correct formulas down. Sometimes people, when they have to predict, for example, what happens on the other side of the equation or the arrow, they try to balance and write the chemical formulas down. And they usually will end up writing the wrong chemical formulas down because they're trying to balance while they're doing that. And usually what will happen is you'll be there all day trying to balance something that will not balance because you did not start with the right formulas. So probably in our cases, 9 times out of 10, you'll have all the formulas given to you in the equation. You just need to balance it. But just in case you get something that is words, you want to make sure always you start out with the right formulas. And that goes back to nomenclature, like we talked about in the last 2 chapters, how to write the right formulas and sort of name things. When we balance an equation, so again, if we have something like H2O in an equation, the only way that we balance it is by changing the coefficients. So only the numbers that come in front is what we change. We never change any of the subscripts because, again, if I change the subscript, say, to a 4 for some weird reason, that is no longer water and probably nothing that exists. So you never change any of the bottom numbers. Also, you never do anything weird that people always want to do, like I'm just going to put a big number in between. So you never do any of that as well. So the only thing that you should change when you go to balance an equation is those coefficients that come in front. You want to continue to balance the equation by changing the coefficients until essentially you have the exact same number of elements on each side. So just like we saw on the previous slide, you want to have, example, 4 hydrogens on the left, you should have 4 hydrogens on the right. You have 6 carbons on the left, you should have 6 carbons on the right. Again, they may not be in the same sort of formulas, but you just need to have the same number. Once you've balanced everything, there are 2 main rules that you have to follow. One is it must contain all whole numbers for those coefficients. So in a properly balanced equation, all the numbers that come in front of the formula should be whole numbers. And it should also be, the second part of that, the simplest set of whole numbers. So for example, let's say that you had 2a plus 4b represents, we'll go with 6ab. We'll just assume that this is balanced. So assuming that this is a balanced equation, and although it is balanced, they're all whole numbers, we could go through and divide each of these numbers by 2. And then you should do that, and you would get something like a plus 2b gives us 3c. Yeah? And this would represent the correctly balanced equation. This one would not, represent the correctly balanced equation. So this sometimes can happen because sometimes people will see sort of larger numbers and you can balance the same equation with sort of bigger numbers. But if you can reduce down not just one or two of them, but all of the coefficients by a common number and still get a whole number, you should do that because that would be the correctly balanced equation. Most people do sort of a trial by error, kind of add some coefficients and sort of see what happens. So let's take a look at this one. And sometimes it's helpful when we're balancing equations to make a little table. So nitrogen, oxygen, hydrogen are involved. And on the left-hand side is our reactant side. On the right-hand side is our product side. And sometimes this table is helpful because it kind of gives you an idea as to where to go and kind of work through the problem. So if we go on the left-hand side, we have 1 nitrogen. Right-hand side, we have 2. Left-hand side, we have 1 oxygen. Right-hand side, we have 1 oxygen. Left-hand side, we have 2 hydrogens. Right-hand side, we have 2 hydrogens. And in this case, everything is balanced except for the nitrogens. So that kind of helps us decide that the nitrogen is probably the best place to start. So since I have 2 nitrogens on the right, only 1 on the left, I could fix this again by putting a coefficient in front. And when I do that, that's going to change my count over here. I will now end up with 2 nitrogens. Oxygens is 2 times 1, which would give me 2. And hydrogens will still remain as 2. Any questions on that? And this is very common. What happens is we fix one thing but kind of mess up everything else. So what we see is we fixed the nitrogen, but we did mess up the oxygen. So the table helps us decide the next thing that's probably easiest to do is to come over here where we have our oxygen and also put a coefficient in front, which would be a 2 in this case. This gives us 2 nitrogens on the right-hand side. 2 times 1 is 2 oxygens. And now we have 2 times 2, which is 4 hydrogens. And we can see now that we fixed the oxygens, but now we have messed up the hydrogens on the left-hand side. So we can finally fix that by also adding a 2 in this case. And that will get us 2 nitrogens, gets us 2 oxygens, and 2 times 2 is 4 hydrogens. And this would represent the balanced chemical equation. Again, the only thing that we changed were the coefficients that came in front. We did not change any of these small numbers or anything like that. Any questions on how to balance that equation? Okay, so I think you got one here. Why don't you take a moment and balance this one? Take a minute or so, and then we'll talk about it. Okay, let's take a look and see how we're doing. So if we come over here, left-hand side, we have 3 carbons. Right-hand side, we have 1 carbon. Left-hand side, there is 8 hydrogens. Right-hand side, there are 2. And let's see here, oxygens, we have 2 over there. Oxygens, there are 2 here and 1 more over here, which gives us 3 total. So again, looking at this table, not too much balance, but probably the easiest thing to start with would be the carbon. So to start with the carbon here, we would put a 3, and that's going to give us 3 carbons. It will also, on the right-hand side here, give us still 2 hydrogens. And in terms of oxygen, we now have 3 times 2, which is 6, plus 1 more still over here gets us to 7. In this case, we fix the carbon. We still are not good with hydrogen and oxygen. To fix the hydrogen, that would probably be the next easiest. We could put a 4 here. When we put a 4 there, again, we still have 3 carbons. Hydrogens, 4 times 2, which is 8. And oxygens, we're now up to 6 here. And we have 4 more over here. So 6 and 4 is 10 oxygens total. At that point, we can now fix the oxygens by coming back to the other side and putting a 5. That gives us 3 carbons, 8 hydrogens, and 5 times 2, which is 10 oxygens. So this would be balanced with the 1, 5, 3, and 4 as the coefficients. Much like everything in chemistry, even though this coefficient is 1, when we balance equation, we typically don't write the 1 in. Not necessarily wrong, I guess, but usually don't put the 1 in front or anything like that. Any questions on this one here? Okay, so let's take a look at another example, I think. So why don't you give this one a go, see what you come up with. Take a minute or two. Okay, so let's take a look. So following the same approach, we're going to sort of make a little table here. On the left-hand side, there are 2 borons. Right-hand side, there is just 1. Oxygen on the left, there are 3 here plus one more over here gives us 4. Oxygen's on the right. This 3 does need to be distributed to both of the things that come into here. So that would give us 3 oxygens on the right-hand side. For our hydrogen, we have 2 on the left. And for our hydrogen, again, with that 3 being distributed, will also give us 3 on the right-hand side. So not a lot to work with here on the right-hand side. So it is easy to fix the boron by putting a 2 in front of it. When we put a 2 in front, that does give us 2 borons. Now for oxygen, as I said, we do distribute that 3 in, but then we also need to distribute out to the coefficient. That's 3 times 1, which is 3, and then 3 times 2, which is 6. Same thing for the hydrogen, 3 times 1, which is 3, then distributing out for that hydrogen in terms of counting. That will give us 3 times 2, which is also 6. So if you do have something with parentheses and it's got a little number on it, you need to distribute in and then distribute out. And that means that obviously we balance the boron. Oxygen and hydrogen are not so good. We obviously do not want to change anything on the right-hand side. Again, that will kind of mess up everything that we already just did. So the next easiest thing to balance probably would be the hydrogen. We could simply put a 3 in front. Again, we chose hydrogen here because it's only in one thing on the left-hand side, not like oxygen, which is in 2 things. Boron on the left is 2. Oxygen is 3 here. And then also, again, 3 times 1 is 3 more. That gives us 6, which actually fixed the oxygen. And then 3 times 2, which is 6 in that case for the hydrogen. So that also balances it as well. Any questions on that particular one there? Okay. And let's take a look at another one here. All right, so why don't you give that a go? We'll talk about it in a minute or so. All right, let's take a look and see how we're doing on this one. Left-hand side, our nitrogen is 1. Right-hand side, nitrogen is 1. Left-hand side, we have 3 hydrogens, and right-hand side, we have 2 hydrogens. Left-hand side, we have 2 oxygens, and right-hand side, we also have 2 oxygens, again, 1 here and 1 over here. So it doesn't look too bad. Looks like most things are balanced except for hydrogen. So that obviously is the place where you'd want to start in this case. In this case, though, we have 3 on one side and 2 on the other side. So our common number there would be 6. So in this particular case, we would actually have to add numbers to both sides to start. So to get our hydrogens on the right to 6, we would need a 3. To get our hydrogen on the left-hand side to 6, we would need a 2 be put in front of there. That gives us now 2 nitrogens on the left. Hydrogen, 3 times 2 is 6, which is good. And we still have 2 oxygens on the left-hand side. On the right-hand side, we have 1 nitrogen. We have 3 times 2, which is 6 for our hydrogens. And then for our oxygens, we have 1 here. But now we have 3 more over here. So that is going to give us 4. So much like what happens, we managed to fix hydrogen, but mess up everything else. So the next easiest thing to do would be to put the equation back. That's good. Would be to fix the nitrogen. So we would want to put a 2 there. And when we do that, that gives us 2 nitrogen, still 6 hydrogen. And now for our oxygens, again, we need to distribute. So we got 2 oxygens there, plus 3 more here, gets us to 5 in this case. All right, so at this point, when we look at, we balance the nitrogen, we balance the hydrogen. Now we see the oxygen. We have 2 on the left, 5 on the right. We obviously don't want to touch any of those other numbers because we'll mess everything up that we just did. So clearly, to do this question, the best move is probably to go to the next question. No, I'm just kidding. The next thing that we need to do is figure out how we can basically turn this 2 into a 5. So one way that we could turn this 2 into a 5 is to use something like 5 divided by 2, or 5 halves. If we take 5 divided by 2 times 2, that gets us 5, which is what we need. So if we look at this on the left-hand side, we have 2 nitrogens. We have 6 hydrogens. And again, 5 halves times 2 is 5. So this equation is balanced, but you may say to yourself, wait, there was that rule at the very beginning that said when we are done, all of the coefficients has to be whole numbers, right? And clearly 5 halves is not a whole number. So this demonstrates a pretty good point. You can use a fraction to balance the equation, but this equation is not correctly balanced at this point. We do need to clear the fraction. So to clear the fraction, you need to multiply not just the fraction, but the entire thing by the denominator, the guy on the bottom, right? So we're going to multiply everything by 2. And if we do that, that gets us 4 NH3 plus 5 halves times 2 is 5 O2. Multiplying that 2 to the other side gives us 4 NO plus 6 H2O. And if I didn't screw up anything, we should still be balanced. So if we look at this, that is 4 nitrogens on the left-hand side. We also have 4 nitrogens on the right-hand side. We have 4 times 3 hydrogens on the left, which is 12. We have 6 times 2 hydrogens on the right, which is 12. We have 5 times 2 oxygens, which is 10. We have 4 oxygens here and 6 more here, gives us 10. So this is a very good example that although you cannot finish a balance equation, like call it done, with a fraction, you can use a fraction to balance an equation. The only thing is you do need to clear it when it's all said and done. Questions on how to do that? Now, sometimes people will ask about the fraction. The fraction is pretty simple. So for example, we use 5/2 for O2. And the way you can choose the right fraction is, if you remember, the top number is the number we needed. So we needed to turn that number into a 5. So we put the top number as the number that you need. The bottom number here should match that number there. And that's the way you could kind of choose the correct fraction when trying to balance equation. A lot of times this will occur when you have, like we do in this problem, oxygen, for example, in 2 different guys, but only O2 are kind of the natural form of oxygen on the left-hand side there. Any questions on balancing? So again, the correctly balanced one for this one is the one that's boxed, the one with all whole numbers, but you can use a fraction to balance an equation. You just got to clear the fraction when it's all said and done. Any questions on any of that there? Okay, we will stop here today. A couple of things. I guess I did forget. Next week is spring break. So I believe Dr. Tyler is not doing lab or anything like that during spring break, but she'll still be available to contact her if you have questions, I think. So we will follow the same here for lecture as well. So there will be no live lectures next week. We'll observe spring break. But if you still have questions, you can still ask and stuff like that. I would still just ask you to continue to check Canvas. There may be some stuff posted on there and stuff like that. But we won't do any live lecturing. But you know, if you need to contact me or anything like that, I know you got a message that it was canceled. So we're not going to actually probably do live lectures or anything like that. I haven't decided yet. I may post up some lectures for you to watch during spring break if you want on some of this topics that we're talking about right now. But we won't have any official live lectures, I think, during next week. But I will still be available to contact if you need to email me or anything like that. I may still be posting some stuff up on Canvas and everything like that. So we're going to follow the same thing as Dr. Tyler, since she's doing your lab, and I believe that's what she conveyed to me. Unless she changed her mind, then obviously do whatever she says. But my understanding is that's sort of what she's going to be doing as well. So still check Canvas and stuff like that. I may even put up a recorded sort of lecture on some of this topic just to kind of keep us on track and stuff like that. But we won't do live lectures next week. This lecture will be up hopefully by tomorrow at the latest. Again, it takes a little bit of time to sort of process these and get them ready to get up there, but hopefully by tomorrow at the latest. Maybe by tonight it might be up there, but by tomorrow hopefully you'll be able to find this lecture up there as well. The lecture notes are up there right now, so again, if you haven't found them, again, the lecture notes are up there right now, but this recording will be up again probably hopefully by the end of today, but by tomorrow the latest. Any other questions on that? So again, we're not going to do any live lecturing next week. I may post some type of recorded lecture that you can watch to sort of stay on track and stuff like that. But we won't do it at the live time. We'll resume live lecturing after next week at our normal time at 7:35. In addition, the exam was scheduled for the week after spring break on our schedule. So it will obviously be moved, and it's probably going to be moved to the following week from when it's scheduled. I don't even know what that date is, but so not next week, not the following week like when it was scheduled, but it'll probably be moved to the week after that and stuff like that. So don't email me and stuff like that scared that the exam's going to be when we come back. Technically in a week or so, it will probably it'll be moved up or be moved back and stuff like that. Any questions on that? I think that's like April something, 20 something, maybe the week of that, April 22nd ish, something like that, I think is when the next exam will probably be. Any questions on that? So I think that's going to be the plan for next week. No live lectures, but I might put up some recorded sort of lectures on this, on the maybe some of this chapter, the rest of this chapter, again, just to kind of keep us on track, and you could kind of log in and watch those and stuff like that. Any questions on any of that type of stuff? Okay, then have a good one. Again, we'll be back virtually a week from Monday. Other than that, make sure you still continue to check Canvas for any type of updates. Have a good one. Bye-bye.